All right, so this is a video for a question answer that Steven sent in. And this is actually a good test to see if this is a good way to go about answering everybody's questions. Steven's working through a few of the book problems from the Stewart text. These come out of 9.1. So these are 9.1 questions. And Steven just took a snapshot in the book and sent me the two questions he had. He did a good job outlining what it was he was looking to find. So he said on number 5, he was able to show that both A, B, and C, or all three of those, don't work, but he's unable to show why D does work. And that's the answer listed in the back of the book as working. Just a quick example of why a problem like A wouldn't work. If you have our differential equation listed as y double prime plus y equals sine of x, what you're needing to do is plug in a second derivative and the original function. So we know the original function, that's sine of x. And the second derivative for sine, so if I just go over here and I do we'll just write the function, and then the first derivative would be cosine, and the second derivative would be negative sine. So then we're going to take, we already plugged that in, and we're going to plug the y double prime in. And then on the left-hand side of the equal sign, we've got negative sine and positive sine. When you add those two together, you get 0. And on the right-hand side, you have sine of x. Now, sine of x does equal 0 at certain x values, but it's got to work for all x values for this thing to be true. So what we just showed, because the left and the right are not equal to each other, is, and let's get a separate color here. We showed that these two are not equal, therefore A does not work. So you can likewise do a similar deal with B and C and show that they don't work. But Steven's question was specifically about part D. So he's saying, why does part D work? So if we look at part D, so I'll kind of box this out here. If we look at part D, we've got y equals negative half x cosine of x. And this derivative is going to get a little more intensive than the previous one because it's got two pieces. So we're going to need product rule. So we've got y prime. So we'll derivative of the first, that's a negative half, times the second is cosine of x, plus the first, which is a minus 1/2 x, times the derivative of cosine, which is negative sine of x. And I'll clean that up a little bit. I've got negative half cosine of x. Negative times a negative is a positive, so I've got plus half x sine of x. That's the first derivative. So I've got my original function, which I'm going to need, just like I did in the previous one. Got my first derivative, but this doesn't have space for a first derivative, so then I need to take a second derivative. That's going to get, and I'm going to use all this space here, that's going to get a bit longer. This first one, we have negative half cosine of x. That derivative is just half sine of x. So we get a negative multiplier, which offsets the negative. Second one, we've got to use the product rule again. So the derivative of the first is half. Leave the sign alone. And then we're going to go plus half x times the derivative of sine, which is cosine. Half sine x, those two can combine to be a full sine of x. So we have sine of x plus half x cosine of x. There's our second derivative. So there's our second derivative. So we've got our second derivative, we've got our original function. Those two things are then going to get plugged into our differential. So let's see if I can fit that all on one screen. I think I can. Y double prime plus y equals sine of x. So I'm going to take, and we'll switch colors here just because we can. I'm going to take that and put it in for y. I'm going to take this one and put it in for y double prime. So for y, I have negative half x cosine of x. That's what y equals for this particular one. And again, that just is literally coming from right here. That's what they're giving us. And then by taking the second derivative, I get this longer expression. And what I see happening here on the, and I guess you get the right-hand side, on the left-hand side is I have these two pieces that are the negative of each other. So they cancel out, and we're left with just sine of x by itself. And then, of course, we have sine of x on the right-hand side, and those two are equal. So that's the first of two questions that Steven asked, and I'm going to just minimize this and jump to the next screen. Let's see, how do I pull that off? Here we go. So he also screenshotted this picture of the book, and actually if you're doing this, I know the big book's there, and I think he probably got the bend out of the book as much as he could, but you can see how his picture on number 13 kind of arcs a little bit. on the book spine. Just if you do send me a photo, try to flatten it out. But this is fine. We can read it. If it got any bendier, I think we'd be in trouble. So this one's a matching problem. So it says match the differential equations with the solution graphs. So it's kind of a different way to word what's happening. And I'm going to, again, switch back to black. They've given you 4 differential equations. They've then given you 4 y equals graphs. So they've given you 4 differential equations. Those are A through D. They've given you 4 solution graphs. So they're not giving you a slope field. They're giving you the line that you would trace through a slope field. So these are Roman numerals 1 through 4. Those crazy Romans using their different numbering system. So we've got our 4 differential equations that would create slope fields. We then got 4 red lines or red curves that are going through those slope fields. And they didn't draw the slope field. They just drew the red line as if they started from some initial condition and traced through it. So the idea here is you're looking at the slope, the differential equation, which is the slope, and you're saying, what does it say about this particular function? And then in each case, you're kind of doing a ruling out process. So as a for instance, if you look at probably the most straightforward solution curve is on number 2. You get a solution curve that is quite clearly a linear function. And it's a flat horizontal line through the origin. So on number 2, we are most definitely getting y equals 0. There's no question of that. And notice on that one, what that means is that the derivative has to be 0. And so if we're looking at this, the derivative is 0, meaning it never increases, it never decreases. That has to match one of these functions. And you're just going to go through each of the functions and try to figure out where it matches. So as a for instance, it's not going to be A. So it cannot be A. Because on A, no matter where you are on the graph, no matter what x and y values you plug in, you get a positive slope. So on A, again, right up here, if you square something, an x value, you square a y value, you add them together, you add a 1 to it, there is not a point on a Cartesian coordinate plane that would give you a 0 slope. So we can rule out A. So A is not an option. And we're going to go through each of them that way. But of course, as soon as we match one up, then we can shift gears and it becomes easier to do the next one. So let's see, what else could we look at? In looking at the second one, potentially it would work, right? Because y equals 0 is the place where x is 0. So y equals 0, no, the x values are right. So sorry about that. My internet just skipped out on me, which is going to be one of the issues here. So just getting back to this particular one. Again, we ruled out A. If we're looking at B, we're looking along the y-axis. So x is changing, y is not, which means, and it's times E. So anything times E, let's see if the pen's there, there we go. E to anything, no matter what it is that's up there, is positive. And then when x is bigger than 0, you have to have positive numbers. Even when y is equal to 0 here, you have to have a positive slope. So in the first and fourth quadrants, this thing, the B, always has to be positive. So first and fourth quadrants, the graph has to have a positive slope. And this one most definitely doesn't have any positive slope. And then in part C, every piece of that thing is positive. The 1's positive, the 1's positive, the e to the x squared plus y squared is positive. So this one's positive everywhere. So a lot like A, that one's positive everywhere. This one, just to be clear, it would be negative in the, let's see, it'd be negative slope in the second and third quadrants, and it'd be positive here and here. I'm just writing that up there because I think that's going to help us match the other ones up. And so by process of elimination, what I've just done is slice through A, B, and C, which means the answer on number 2 is D, or D matches with 2, I guess, however you want to look at it. So if we're gridding out A, B, C, and D as our answer set, D would be 2. And again, to get there, I just did a process of elimination. Now, why that works? Everywhere along this line, y is 0. That's the equation for it. If I pop a 0 into that slope equation, I'm going to get sine of 0 cosine of 0, no matter what x equals for any x value. So the derivative is sine of 0, cosine of 0. Well, sine of 0 is 0, cosine of 0 is 1, and so what that means is I've got something that works. I've got something where if I plug that into the expression, I get a slope of 0 all the way along the line. And so through that process of trial and error, I can come to knowing that D matches with 2. Hopefully also by diagramming these out the way I have, saying, okay, slopes are always positive, slopes are always positive, and then I've got this negative, negative, positive, positive, I can do some matching. Just using that structure as I look at the remaining options, 1, 3, and 4. I can see that in 3 and 4, the slopes are positive everywhere. So 3 and 4, slopes are positive everywhere. In problem 1, the slope is negative here and positive here. Of the 3 remaining options, there's only one that matches with that, and that's B. So for B, I know my answer has to be 1. And again, this is trial and error. This is not coming up with a specific solution. You don't need to know what the y equals is, except I would argue on number 2, that's a pretty obvious y equals. You could make the argument that number 3 was a cubic, but maybe it's a tangent, or maybe it's some kind of adjusted cubic, or a 5th power equation. Like, we just don't know. So you don't need to come up with it. You just need to say what's happening in the picture. This one now is going to get a little trickier, I think, but maybe not. Maybe not. I'm going to just, because if I'm looking at what's left, I've got A and C. A looks a lot more straightforward to me. So C's got this fraction going on. It's got an E in it. It'd be great if I could just come up with A, and then I know that C by process of elimination is what's left, and I just need to verify it works. So as I look at A, everything's got to be positive, but that fits both graphs. And again, what I'm down to now are 3 and 4. So now I'm going to say, okay, well, x squared and y squared, as x's and y's get bigger and bigger, in other words, as I move up and to the right on the graph, because that's where x's and y's get larger and larger, as I move up and to the right on the graph, that is accelerating the slopes at a quicker and quicker rate. So I need to find the remaining graph that moves up and to the right at a faster rate. And that's going to, I guess, to me, clearly be 3. But the reason I see that is bending upwards versus bending downwards. Still positive, but the difference is this one's getting more steep as x's and y's get bigger. And then you can verify in the negative direction, same thing's happening, right? It's getting more and more steep. It's a still positive slope if you draw in a little tangent line segment. Those are all positive. But when we square things, of course, you're making the negatives positive. So when we're way down here and way up here on this graph, we should see steeper slopes. That matches with A. So A matches with 3. And then by process of elimination, C has to be 4. You can verify that if you just think about what a fraction does. The bigger x and y get, the bigger the denominator gets. It never gets negative, so the whole thing's always positive. But as you get further and further away, as you get out here and out here, that denominator in the slope is getting larger and larger. So I'm taking 1 divided by a really big number. I'm nearly getting to 0, and you can see these slopes starting to flatten out. And the steepest slope occurs right in the center. And the reason it occurs right in the center is that's where the denominator is the smallest. And so on this one, it's C matches with 4. So this process of elimination and kind of matching the general structure of the solution graph to what its slopes look like is what they're after on this one. So Stephen, hopefully this helps, and others, hopefully you can get something out of this. I'll post this to the website, and you can enjoy your 15 minutes of calculus. Actually 14 minutes of calculus, but who's counting?